Hello folks, it's Federico here, and in this video we're going to finish the falling sand code, at least to a level that is acceptable and fun to play with. So the things we are doing in this video is we are adding this grid on top of our simulation. We are placing the particles with our mouse, and then we're using typed arrays in JavaScript to speed up the code. As you can see, I'm now at 120 frames per second, around 100 frames per second, and this would have not been possible with so many particles using just set cell and get cell without using typed arrays in JavaScript. So it's going to be a pretty long journey, but I'm sure you will find value into it. And as Leonardo da Vinci used to say, it's not who begins, but who keeps going. So let's keep going. Okay, so this is the patcher as we left it in the previous video. So the first thing we want to do is to put those particles in this virtual grid, which mirrors our jitter matrix layout, with the mouse. So instead of using this message set cell 1, we just want to click with our mouse somewhere and make sand appear where we click. So first of all, let's visualize this grid so we have a better idea of what or where the grid cells are. So in order to visualize the grid, we can use a GGL grid shape. And this must be shape plane. We want to have grid mode 0. Or first, let me show you how it works with the default grid mode 1 and poly mode 1. So, right, this will be our grid. And as you can see, it's divided into triangles, but we want to have it divided into squares. So we can use grid mode 0 for that. And now they are squares. Now, as you can see, it doesn't perfectly match this doesn't match at all our sand grains. And that's because by default, the dimensions of these are 20 by 20. And we want to have the dimensions to be the same as the grid size plus 1. Because if we will just have it 10 by 10, it was still not much because it gives us 9 squares, but we want to have 10 squares. So we have to give it dimensions 11 by 11. And there we go. Now it matches perfectly our sand particles. Now let's say that we want to change the dimensions of our grid. Let's actually create a message here with our grid dimensions. Let's say we want to have it 100 by 100. And let's send the grid size with a sender object, and let's receive them here and prepend that with the dimension string. So this will modify the dimension attribute. And of course, we want to have it plus 1, so we should say plus 1. Let's make it maybe 40 by 40. And before we send it here, before we use it for the dimension, we need to do like this. Plus 1. And then scalar mode 1. So it will apply the plus 1 to both the elements of this list. So let's try again. And cool. Now it works. Now we need to modify also the dimensions of the matrix here, our simulation grid. So let's use the dimension here for both these two matrices, right? And we need to change it also inside our JS object, our JS code. So let's do like this. Let's create the grid size. Let's not just declare it like this in our JavaScript code, but let's declare this as an attribute of the JS object, the V8 object. So we can do something like this. We have to use the bar keyword to declare attribute for the V8 object. And let's call it simply grid size. And it's going to be 10 by 10, or maybe let's make it 10 by 10. And then let's say declare attribute. That's a max keyword inside JavaScript, is inside JS and inside V8. So it works like this. We say the name of the attribute, and then we say if we want to have a getter, we will place it here, the function. If we want to have a setter, we will place it here. And in fact, let's place a setter function name here. We will call it set grid size. And then the last value is if we want to save this value with the patcher, which I don't think we want. So cool. And then let's create the setter function. So set grid size. This is our function. And that's going to be the X dimension, and that's going to be the y dimension. And, oh, sorry, I had to say that this is a function, of course. Oh, and it's complaining. Let's stop this Q metro here, so it will not complain it anymore about the fact that the array grid size is missing. So inside this function, we want to update our grid size value with x dim and y dim. And then we also want to change the dimension of our simulation grid. And maybe let's also change the names of those matrices. Instead of calling mat sim grid, we will call it mat grid in. And this is going to be our mat grid out. So the one is the input, and it's kind of read only, and then there is the output, which is write only. And this is grid size by default. And then when we set a new grid size, we want to change the dimensions of those matrices. So dim equal to grid size, and also mat grid out dot dim is equal to grid size. They must have the same dimensions, of course. So let's change our grid size whenever we find it. So just Command D, and then Control V, and that's it. Let's see if our code still works. So let's try that. Let's update the QMatr. Oh, matsim grid is not defined. Of course, we need to change the names of the matrices as well. So matsim grid becomes mat grid in, and mat temp sim grid becomes mat grid out. And I missed a mat sim grid in. Right. Okay, cool. Now let's try again if it works. So let's try to place a cell, and great, it works. Let's set the grid size and try again. And okay, something is not working. And of course, I forgot to set the grid size also here. So for the V8 object, so I had to say prepend grid size. And as you can see here now, the V8 object has a grid size attribute, which is awesome. So let's try like this. Grid size, and cool. Seems like it's working. Can make this a bit faster, and in fact we can actually connect this to the bang from our JIT world. So let's say send, or let's actually call it world bang, and receive world bang here. So let's try again. Pew, that's pretty fast. Another thing we should do before trying to place the particles with the mouse is to change the ratio of this grid shape based on the size of the grid. Because if you have a grid that is not a square, like 60 by 40, as you can see, the shape will remain a square because there is no reason why it wouldn't. Just its dimensions, the number of its vertices are changed, so it's still a square, and we need to account for that. So what we want to do is to get the grid size here, divide the x by the y dimension, so we can just do that with a divide object. We'll divide the first element of the list by the second, and then we can just say pack scale. That's going to be our x scale, and one for the y and one for the z, of course. So not here, but here. And then connect this to the grid shape. And let's see if we now change the grid size. Of course, it will now scale in order to adapt exactly to the grid size. We need to change, of course, also the video plane size. Right. And now we got it. Now we can place another cell here, and it all matches up correctly. I think we should also place always this grid on top of the video plane. So let's say depth enabled 0, and then let's give it a layer like 10. So this ensures us that this grid will always be on top of the video plane where we visualize the sand. Great. Let's now proceed to place the particles with the mouse. So in order to do that, we need to convert the mouse screen coordinates that we get from JIT world into cell coordinates. Right, so let's do that. So the JIT world automatically, whenever we click somewhere with the mouse on the window, it will output the screen coordinates of the mouse position. So the 0, 0 being the top left corner, and the top right corner will be the size of the window. So if we say root mouse, we will get exactly these values. And the third value here is if the mouse is clicked or not. And then we also have modifiers like command or shift. So that's pretty nice. So we just need the mouse coordinates though. So we will just unpack the first two elements of this list, which are the X and Y coordinates. So what else we need is also the size of the window. So we can get that using the get at object, and this will give us the size of the window whenever the window is resized. So let's also unpack here the X and the Y. So let's also receive the grid size here and unpack also the Y and the X and the Y. And the naive way in which we can scale the mouse coordinates into grid coordinates is simply to use, simply to use the scale object, or even better, the Z map object. And to say, let's scale 0 to, I don't know, I would just pick a default the size of the window, 0 to 319, just scale it to 0 to basically grid size -1, which let's say is 60, which is 59, right? So we need to change this maximum value using the grid size, and then we need to change the maximum input value. Oh, sorry, this was the output minimum. I need to change the output maximum, and then we change the input maximum using the window size. So let's see if we do that. Let's bang here. Let's resize the window. So we update all the variables here, and then let's go with the mouse. And as you can see, it is wrong because, so if the window is the same size as the grid, then it works like this, right? Although we actually need to put integer number after that because we only care about integer numbers, right? So 0, 1, 2, 3, and so on, and this will be, and so this will be 0, 1, 2, and the last the last column will be 59, which is correct. And for the Y, we will do the same thing. So I just change this to 240, and this to 39, just to understand that this is the X and that's the Y, but it doesn't matter because we anyway change those values with these variables. And sorry, not here, but here, and this goes here. And then let's bang here to get the size. Let's bang the grid size and let's see. Oh, actually, it doesn't need to be -1 because the integer value will anyway be the closest smaller integer. So, right, we don't need to say 39. This would actually be 60 and 40. But as I say, it doesn't matter because we update this with the grid size. So let's see. It will give us 39, 59, and all the coordinates in between. So, which is great if the window has the same size as our grid, but if we resize the window and it doesn't cover the whole grid, then we got a problem because this will be coordinate number 6, 0, which is wrong. So the Y, it's always correct, but the X is wrong because the X gets modified by the size of the window. So this will be like, should be coordinate 0 on the X, but it's actually 7, so it's clearly wrong. So we have two possibilities now. Either we modify those coordinates to account for the empty space here, or we change our grid size according to the size of the window, and we just decide how many squares we want on the y-axis. So maybe this is the nicest way to do that. So when the window will, so the grid will always cover the whole window. So in order to do that, what we want to do is to decide how many squares or cells we want on the y-axis. So let's say we want 40 squares on the y-axis, and then we multiply this value by the ratio of the window. So this would be again the ratio of the window. Let's try to put some comments here so stuff is a bit clearer. Ratio of the window dimension. So in this case, this will be like 1.67 something. So we need to multiply that by how many cells we want on the y-axis. So, and then we need to use that as the X grid size. So let's get rid of this. So let's not send grid size from there, but from here. So this will be the X output maximum, and that will be the Y output maximum. Right, and this grid size then is basically the result of 40. It's basically a list with 40 and this value here. So let's see what we get. 6740. Let's try to change the size of the window, and as you can see, it's working. It will adapt the window to the... Unless, of course, the window size on the x-axis is not a perfect multiple of the amount of squares. In that case, we get this base, which is also wrong. Okay, so in order to account for this space, I've found an empirical solution, which is probably way too complex than it needs to be. Definitely, that's the case, but it works, so let's implement it. So basically what do we need is the fractional number of the grid size that is beyond the integer number 80 in this case, for example. So one way to do that is use the modulo operator. And in order to do that, we have to trigger this number in this exact order. We first need to set this, the integer of that as the module values. So this will be I. And then we need to send these as the value. And let's see if this works. Yeah, exactly. We get the fractional part. Cool. So let's call it, this is the excess of squares on X dimension. Something like that. And then we can scale that. We are going to remap this from 0 to the, actually like this, from 0 to the size of the X, from the X number, from 0 to the X number of cells, and then we remap it from to 0 to 1. So we get kind of how much percentage of the whole size this is. So let's use that as the maximum I output value. Could use also ZMap as well here. And this is going to, sorry, this is the I input value. Right, and that's the input. And let's see if this works. 0.03. We need then to multiply that by the X size of the window. Right. So, and in order to do that, let's actually trigger this list in the specific order. So first it will go here right and do all these beautiful things, and then we'll go here left and do all this other stuff. So we preserve the order of the operations here. And we need to multiply that by that. So in this case, it's like 4.137, and I think we should subtract this value from the X mouse position. So let's see if this works. Let's try to get one with a bit of space. So that will be 0 and still 0 here, and then it should go to 1. Right, I have to divide this by 2. I have to divide this by 2. That's kind of the, because we have a bit of space on X on the left side and a bit of space on the right side. So let's try that now. Now I should go to 1. And at the end here should be 67. Yeah. Okay. So this works. As I said, I'm not sure this is the I'm definitely not sure this is the fastest way of doing that, but it works. So we'll take it. And then let's pack that, let's pack that as the cell, so mouse cell chords. And of course, these are 2 integers. So let's use a trigger object here and trigger an integer and then a bang to the pack. And then let's say send mouse cell chords. Let's actually send only the integers without the, so we don't even need a bang here. We just do like that. So we just send the pure integer values without any name attached to them. And let's hide all this mess under the carpet in a sub patcher. So let's call it this remap mouse chords to cell chords. The get attribute needs to be outside because it needs to be actually connected to the JIT world. So let's see, didn't work. Oh, it looks like it broke stuff for us, and that's because we need to also, let's create an inlet here. This will be the Y amount of squares. So squares or cells on Y dimension. And this will be input from the outside. This will be the number 40. And let's load bang. We can have more or less if we want. So let's try to have, for example, 20 of those. And great. So every time we change that, we should also bang the sizes. So let's do like this. Maybe let's put it inside the sub patch. That's going to be a bit more nice. So that's the window dimensions here in the second inlet. So we can also use zil-reg to save this list, and then every time we input a new dimension for the Y, we just bang this list again. So let's see. Let's make it 100. Okay, cool. So it seems to work. Great. Well, this took quite some time, at least on my side. And I don't know how short I will manage to cut it in editing, but it took me quite some time to get to that solution. So let's copy that mouse cell chords. I always make these somehow something changed, and when I rename objects, there is not the space anymore that I was used to have. So let's just here unpack those two values. And again, let's simply, this is going to be the X, that's the Y, and I think we want to bang as well here the set cell to be completely sure. Let's do that. Unpack it and then bang the X and the Y. And look at that. It works. I am as much surprised as you probably, but looks like it's working. So great for us. Let's make this bigger. Every time we modify the window, of course, the matrix gets reset. So we cannot modify the window and keep the state, at least not at the moment. Okay, cool. So let's go inside JavaScript now and add a bit more rules. So we will make the send fall on the right and on the left if it doesn't have anything on its right or its left, because at the moment it will just stay on top of every send square that it meets. So let's do that. Let's go inside JavaScript and in the update function, let's define the coordinates of the cells as variables. So we will have like current cell chords, or let's say like chords current. That's going to simply be I and J. Then we got chords below. That's going to be I and J plus 1. Then we got chords below right. That's going to be I plus 1, J plus 1. And then we got below left. And we're simply going to be I minus 1. So if grid size, if J is less than grid size minus 1, so if we are not on the last row, then do that. Cell below, that's going to be get cell chords below. And current cell, yeah, we can also change chords current. So if cell below it's empty, set cell to the chords current or chords below material send. Okay, now if that's not true, let's say else, so if the send is filled, so if cell below equal materials dot send, so if it's actually full of send, let's get the content of the cells on the below left and below right. So const cell below left equal mat grid in dot get cell chords below left, and of course the first element of this array, and then call cell below right, it's going to be chords below right. And so if, let's just say that it will always go left if left is free, and then it will try right. So if cell below left equal materials dot empty. Let's set the current set 0 on the out grid, and then we set the chords below left to materials dot send. Else, if cell below right it's equal materials dot empty. So if the left is filled but the right is free, we say we set the current cell to 0, and then we say chords below right material send. Okay, so let's give these a try, and okay, we need to first bang again on the size, and it looks like it's working. Looks pretty much. Oh, we encountered an error where we went outside the grid size. So this should be actually prevented. Oh, right, because cell below right is beyond the borders. We can probably fix it here. So by saying and I is greater or equal than 0, and I is less, or yeah, it's basically less than grid size 0. Okay, let's see if that fixes it. This doesn't fix it. So why is that? Oh, because it's not enough. We need to say when checking for the cells below left and right, we need to check that they don't go beyond the boundaries of the grid. So is cell below left equal materials empty. So let's say is cell below left equal materials send and chords below left 0. So basically the x component is greater equal than 0, and chords below left 0 is less than grid size 0, and we do need to do the same with chords below right. Well, actually with chords below right we should just check that this is greater than 0 and not that it's actually less than the size, and also we should not check that chords below left is greater than 0, because it's always greater than 0. No, sorry, the other way around. So chords below left we need to check if it's always greater than 0, but not if it's less than grid size, and we need to check that chords below right is less than grid size 0. Okay, let's see if that did the trick. Grid size, and it seems to have done the trick. Okay, great. So just to be sure that you got everything, I was not covering the code with my face. This should give you the whole view of the thing. Okay, now we almost finished. I just want to show you now how to use the typed arrays in JavaScript V8 to speed the things up, so to make this much faster. And in order to do that, we can check with a much bigger grid size. So let's try like 100, and then this will give us a lot of squares, a lot of cells. And as you can see, the frame dropped pretty dramatically to 29, right? And so let's introduce typed arrays. So let's go here and let's create two variables here. Let's create with let, because I'm not sure we want to modify it, but basically this is, let's say, typed array grid in, it's equal to, and I'm copying from my own code, so sorry if I'm looking sidewise, float32 array, and this array is going to have the grid size 0 multiplied by the grid size 1. So these typed arrays in JavaScript are used, it's not a max only thing, it's a JavaScript thing, and they are used to access raw binary data as an array in JavaScript, and that works well in max with matrices, because the matrices now have a function which is copy array to matrix and copy matrix to array, which then access directly the binary data from the array, and is much faster than using get cell and set cell. So I'll show you in a second how this works. This is going to be array grid out, and it's going to be, of course, the same size as the other one. And when we change the grid size, we also want to change the size of the, I want to basically redeclare these arrays. I don't know if there is actually a way to change the size of those without recreating them, but we can just recreating them when we use the set grid size, the grid size attribute when we modify it. So these arrays are one-dimensional, so we cannot have x and y. We cannot access them with I and j. We can only access them with a single scalar value. They are one-dimensional, so that's why they need to be the grid size 0 multiplied by the grid size 1. And if we want to access them, we basically need to modify our coordinates, because this is not anymore I and j. As I said, this is going to be, let's write it again, then I will comment the old one. Chords current is going to be j multiplied by grid size 0 plus 1. That's how you transform a two-dimensional index to a one-dimensional one. You get the y chord multiplied by the size, the x size of the grid, and then you add, sorry, not I, but not 1, but I, right? So this all makes sense if you try to visualize it on paper and pen, which I don't have set up at the moment, but if you try to do this on your own, it will make sense. So then we want to have the below chords, and as you can imagine, this is basically just j plus 1 multiplied by that, because we go one row below. And then we got chords below left, and that's going to be j plus 1, but also we got I minus 1, and we don't need to put this in between parentheses because this is just an addition, so it's commutative. Then below right, this is going to be I plus 1. And again, just try to visualize this with paper and pen, and it will make much more sense why this works. So then before doing everything, before doing this update, we want to do like this. Mat grid in copy matrix to array. So we're going to copy the whole content of this matrix into the typed array grid in. So now the typed array grid in contains all the values of this matrix rolled in a one-dimensional array. So this function will write to this array. And then we can access this array here. So every time we were saying get cell, we want to replace that with the typed array grid in, and then chords current. And this is not an array, of course, because this is just a single value. It's not the same thing as with matrices that gives us back an array. So this is current chords, and then again here, typed array grid in, chords below. So we just have to say chords below for the cell below. And I'm first doing the get cells, then we will do it the set cell. So this is going to be, so basically replace every mat grid in with typed array grid in. and then these with the one-dimensional coordinates. Chords below right. Sorry if I'm covering again with my face. I hope that's not the case. Let's just put it like this, full screen, right? And then mat grid out is going to be typed array grid out. So mat grid out. So we're just working on the arrays, right? Let's just select them all and let's replace that with this. And chords current. Here let's do like this, and that's actually going to be equal to materials empty. So we're setting the value in this array. We're not using a function, so we cannot pass it as the second argument to a function. This is just going to be the value of the array. So chords below here, it's equal to material send. Chords below left here, it's equal to material send. Chords below right here, it's equal to material send. And at the end of all these, we don't have any more. Actually, we don't really have a mat grid in anymore. We can get rid of that. Sorry, a mat grid out. We don't have any use for that anymore, so we can delete it. Mat grid out. What we have to do instead is to say mat grid in, copy array, this time array to matrix, and then the name of the array, which is typed array grid out. Okay, so let's go back to our patcher. Let's see what is anyway. It's definitely complaining because copy array to matrix is not a function. Okay. Oh yes, I did write it wrong. Copy array t. So let's see. Okay, now the error stopped. Let's see if this keeps working, and it works. And as you can see, it went back to 60 frames per second. So as we said, much faster. Let's try to go even faster. So let's set the sync attribute to 0 and then the FPS attribute to something high, like 120. And as you can see, it's managing to reach it. And this would have not been possible before by using a get cell and set cell. Okay, there is something wrong. It's not following the. It's not following those right. The other rules, so it's not going left and right, and that's because, of course, these now these coordinates don't make any sense like this. And I think it's fine. We don't need to check anymore because now the coordinates cannot really go above. They cannot really go above the end of the array. I mean, they can, but I think the array will not care. So let's just get rid of this check here and get outer size here. And now it's working again correctly. Let's see if we go to the end. Oh, it will go to the other side, which is, we could prevent that if we want, but I think it's pretty funny. So we will leave it like that for the moment. And I really think that's actually it. Another thing, the last thing I want to do is to create here a function, notify deleted. I noticed it was missing. This will be called when when the patcher is closed. And that's pretty useful because we can then get rid of all the garbage in our code. Basically all the memory that is not being deleted yet. And also in the clear function, if we want to clear everything, we also need to set those, reset those arrays. So let's see. I always need to click here, of course. So let's see, let's click clear and we get an error, of course, because I'm still cleaning those matrices. So this is going to be matgrid in.clear. And again, let's try. Let's click on clear and it clears. Okay, great, perfect. This is working. So thank you very much. I know it was a long journey. I hope it was worth the ride. You can download this patcher as always from my Patreon by becoming a subscriber, and I will see you in the next video. Promise you it's not gonna take so much time as it took for this one. So thank you very much again for following. Take care and see you soon. Ciao.